numerical problems. Okay, so let's look at the first question. Question number 1. Consider a MOS capacitor with 5 ms equal to 0. Then Na is given as 1 into 10 raised to 16 per centimeter cube. Question is, what is the work function psi s of the silicon substrate at room temperature? Okay, some more additional parameters are given, e.g. For silicon is 1.1 electron volt, and then chi is given as 4.05 volts. Then Ni, okay, at room temperature it is given as 1.5 into 10 raised to 10 per centimeter cube. Okay, so this is at room temperature. Then Vt, probably you all know, at room temperature it is 26 millivolt. Okay, so all of these parameters are given for room temperature. How do we find out work function psi s? Okay, so this is basically to test your understanding about the energy band diagram. If you don't understand it, you will not be able to do this. Okay, so this is the first case that we have considered. Phi m is equal to 0 means the difference in work function for metal and semiconductor is 0, which means that you will get flat band when you do not apply external voltage. Okay, you will get a flat band when you do not apply external voltage. So it's a flat band condition, so which is relatively easier to draw. So you have the vacuum level, and then somewhere here you have a phi m, and it is going to be the same level on the substrate side also, which is phi s, and that is what you need to find out. So the oxide layer will have large energy band gap, so that I am showing like this. Then it's a p substrate, right, because it's given that Na is given. So Na means we have acceptor impurity, so that's a p substrate. So if it is a p substrate, your intrinsic level is going to be above. Intrinsic level is going to be above the Fermi level in the substrate. So this is your EFS, this side it is EFM, and then you have a conduction band, valence band, EB, and then this is the difference between EI and EV, which is EG by 2. Same distance above you have the conduction band. So this is your piece, and this is what I call as chi. Okay, and that is also given. So you are asked to find out phi s, which is same as phi m. So from this you can write down, but we need to find out psi s is basically equal to chi, which is given to us, plus as I told you earlier, this is also Eg by 2, Eg by 2, Eg by 2. Okay, the difference between EC and EV is what we call as Eg. So intrinsic level is almost at the middle. Okay, we have earlier shown the expression, and that's a very good approximation. It may be slightly below, but we are neglecting that. So we can write psi s as basically chi, that's one contribution. Then Eg by 2, we are reaching EI, so that is Eg by 2, and plus there is some more distance you need to come down from EI, so this distance. And what is this distance? This we called it as phi b. So plus phi b. So out of that, chi is already given to us, it is 4.05, and Eg is also given to us. We can simply substitute 1.1 there, but phi b is not given. But what other information we are given is Na and Ni. So we know the relationship between phi b, Na, and Ni. Okay, so what is that relationship? If you recall from earlier class, the concentration of holes in a p-type material is given by Ni into e raised to Ei minus Ef. In this case it is EFS by kBt. This I can write, this Ei minus EFS is what I call as Q into phi b. Okay, so this is all energy band diagram, so I need to multiply everything with Q to get the energy. Okay, all the phi's are basically voltages. I need to multiply with Q in order to get energy. Okay, so Ei minus EFS, that is energy. If I need to write it in terms of phi b, I need to put Q phi b there. So it is Ni into e raised to Q phi b by kBt. Now this one I can also write as Ni into e raised to phi b by Vt, where I have taken Vt is equal to kBt by Q. All of this we have seen earlier. So since we have a p-type material, we know for p-type material NPP is also equal to Na. Okay, so this is for p-type material. P-type material which is doped only with the one kind of impurity atom, which is acceptor impurity atom. Okay, so the concentration of holes in the majority carriers is more or less same as the doping concentration. So we have two equations for PP, one is the above one, the other is PP equal to Na. Therefore I can write Na is equal to Ni into e raised to 5b by Vt. So from this the only unknown is 5b. So I can find it out. That is 5b is equal to Vt into natural logarithm of Na by Ni. So everything is available. 26 millivolt into natural logarithm of Na was how much? It was 1 into 10 raised to 16. So 10 raised to 16 per centimeter cube. That unit will cancel because denominator Ni is also in per centimeter cube, and it is basically 1.5 into 10 raised to 10. So this is what we need to find out. So if you use calculator and find this out, you will get it as 0.35 volt. Okay, I am taking this question from a book. We will give the name of the book where you can find this question. The title of the book is basically Semiconductor Devices Modeling and Technology. Author, so others are basically Nandita Das Gupta and Amitava Das Gupta. Okay, so if anybody can get a copy of this book, it is a good reference for this portion of the syllabus. Okay, so now we can find out phi s. So therefore phi s work function is basically, let us substitute everything. Chi is what? 4.05 volt. Then plus Eg by 2. How much is Eg? 1.1. So half of that is 0.55. Eg is electron volt. So if you just divide it by Q, we will get it in volt. So 0.55 volt. Okay, so it should be Eg by Q here. So let me correct that here. Eg by 2Q, because this is in volt, 5B is in volt, Eg is in electron volt, which is energy. So if I have to divide by Q in order to convert that into voltage. So electron volt will become volt when you divide it by Q, but we can use the same value for it. Only the unit is getting changed by division of Q. Plus what? Plus our 5B, which we have just found out, which is 0.35. So if you add all of this, you will get 4.95 volt. So that means in this diagram, our work function for metal as well as the semiconductor is going to be Q into 4.95. Okay, so that is this height from vacuum level to this Fermi level. It is Q into 4.95. So that many electron volt, or 4.95 electron volt you can say. Okay, Q5. If you want to specify that in volts, just say the value of phi s. If you want to specify it in terms of units of energy, then you specify Q phi s as 4.95 electron volt. Okay, so that was first part of the problem. Now more important, so it is the same problem that we are going to continue. It's an extension of this the already stated board. So that's how in the book these problems are presented. Okay, so question number 2. Calculate the whole concentration. Calculate the whole concentration PPS. Okay, so usually I use PP as the concentration of holes in p-type semiconductor, but here S stands for the surface, the interface between oxide and semiconductor, in that point inside the semiconductor surface. So calculate the whole concentration PPS, which can in principle differ from the PP, which is the concentration in the bulk. Concentration in the bulk, we already stated that it is equal to Na, acceptor impurity concentration, but PPS could be different because of band bending. So that's what we are going to look at. So calculate the whole concentration PPS. Also electron concentration. So electron concentration at the same place, that is NPS, and the charge density rho, charge density rho at the surface, okay, semiconductor surface, semiconductor surface for number 1 psi s equal to 100 millivolt, and number 2 psi s equal to 200 millivolt. Okay, so we are given the voltage drop inside the semiconductor. So this is like a case where, so it's a continuation of the early problem. We have phi ms equal to 0. So all that we stated earlier, the parameters that we had, we can take the same parameters, and it is a continuation of the earlier problem. So that's why not much of the parameter is given here, only some additional details are given. So since it is a case where phi ms equal to 0, there will be no bending just when you form the metal oxide semiconductor. When you join the 3 different materials, there will be no band bending because the work functions are same on both sides. But in order to have band bending, what we need to do is we need to apply the external voltage that we have seen in the previous class. If you apply an external voltage, then there will be voltage drop inside the oxide region and in the interface region inside the semiconductor also. So let us redraw or let us draw that case. So now we are going to apply a voltage. Now we need to decide whether we need to apply a positive voltage or negative voltage. Okay, so the way we have explained earlier, when we apply the positive voltage, the metal region, the Fermi level will go down, and that will give you basically a bending in both the oxide and semiconductor interface. So, and that bending corresponding to the positive voltage applied is what corresponds to positive psi s. Okay, that's how we have taken. So that's a convention we are going to use. So we are applying a positive voltage. So therefore, let me put the Fermi level here, and so this is my phi s. Now, as I told you, the Fermi level on the other side is going to be above. Okay, this difference is basically equal to Q into what? Q into VGB. And then what else will happen? Okay, so there is going to be band bending like this, and there will be slight bending in the oxide, in the semiconductor also. So this distance, so this is Q phi s and this is Q phi m, they are same. Okay, that's the case that we are considering. And then you have a oxide region, okay, so this is the EC in the oxide region and this is EV in the oxide region. EC and EV. Okay, so now coming to the semiconductor region, which is the most important part, it is given that we have a bending and the voltage is given. So this is what we call as psi s. Now this bending is going to change the concentration of holes at the interface. Away from the interface, the concentration is going to be Na, which is basically the acceptor impurity concentration. Okay, so how do we draw EI and all other levels? Away from the interface, it's easy to draw. So this is a p-type semiconductor. So you have your EV here, then this is your EI, then same amount if you take upward, you have your EC. Okay, and there is going to be a bending here. Like this. So what is given is this psi s. It is told that psi is equal to 100 millivolt in the first case. So there are two parts again in this problem. Psi s is equal to 100 millivolt. We need to find out what is going to be the concentration of electrons and holes at this point. Okay, so our point of interest is here at this point. Okay, so this is basically the x direction. So we are interested in, suppose this is the origin I am taking O, we are told to find out what is going to be the concentration NPS or NP at x equal to 0. So that is NPS. So let me specify that NPS is basically NP at 0. So that is x equal to 0. And similarly PPS is basically PP at x equal to 0. So this is what we are told to find out. Now away from this bulk we know the concentration, and we need to find out what is at the interface. So how will we find out? Okay, so again the same relationship which I wrote earlier for question number 1, we can make use here also. PP is given by Ni into e raised to E I minus E. So here it is EFS, I have not marked, this is EFS and this is EFM. Okay, this divided by KBT. Now only thing is that if you want to find out at PP of 0, so then you need to just substitute instead of PP which is in the bulk, you have to substitute PP of 0. So then EI of 0 you have to use. Okay, so we are using the general relationship, but now we are saying for the point EI of 0. Okay, because EFS is constant, it doesn't change with x. Only thing that changes on left hand side is x PP of 0, and similarly it will correspond to EI of 0 because band is bending, so EI of 0 is going to be different. If you can see that EI minus EFS is reducing. Earlier it was this much Q5B, but now on the edge it is different. Okay, so how do we do this? So what we can do is can take this equation and then write it as EI minus 0. So what we can do is we can add EI and subtract EI. Okay, so let's do that. EI, so this is at a higher, okay, this level I am talking about, at a large x it is called EI. EI is 0, I refer to the edge. So we are adding and subtracting EI, and then EI of 0 minus EFS by KBT. So that is going to give me Ni into, then I am going to split these terms like this, EI minus EFS by KBT into minus of EI minus EI 0 of KBT. Now this quantity we already know. So that is equal to, so this is what? This is basically PP. So PP into minus, and EI minus EI 0 is what we refer as Q psi S. So if you now substitute VT, we get a very simple expression, that is minus psi s by Vt. Okay, I hope everybody is following me. If there is any doubt or questions, please ask. The notation that I am using, you have to understand. EI, simply EI means at very large values of x, okay, where it is flat. That is what. So this corresponds to flat region. Which is away from interface. So that's the notation. I don't put any x there. X is very large from the origin, whereas EI0 is at the origin, x equal to 0. So where there is a bending and EI is changing, and the difference between these two EI, the original EI position minus the new EI position, so that is what we define as psi s. Okay, q into psi s. Is that clear? Are you with me? Yeah. So it is very clear from this expression that the PP we know it is NA. Okay, so we can substitute that, and this the other factor here, e raised to minus psi s by Vt, that is going to be smaller than 1 because of the minus sign. Okay, so the whole concentration is going to reduce. That is also evident from our band diagram. You can see that there is large separation from the valence band to the Fermi level compared to that in the bulk. The bulk, it is more closer. It is 5b. It is only this much, but here you have larger separation. So larger is the separation. The smaller will be the whole concentration. If it is EI, it will be even smaller. If it is going above EI, again it will be more smaller. So now only just need to substitute to find out the whole concentration. So PP of 0. So this is what we call as PPS. It's given by NA, which is our PP, e raised to minus. So case 1, if I do, you take 100 by 26. Okay, let me just initially write what it is. So psi s by Vt, so which is 10 raised to 16 into e raised to minus 100 by 26, and this comes around as 2.1 into 10 raised to 14 per centimeter cube. Okay, so here unit is per centimeter cube. And similarly, NPS is going to be what? NPS is going to be NP in the bulk multiplied by e raised to plus psi s by Vt. So because whatever is the reduction, same amount by same factor, it has to increase. Okay, so if it is reduced by a factor this, it has to increase by the other factor, so that the product will remain constant. Okay, so that's called law of mass action. Law of mass action says n into P is equal to a constant. So if P p we have already seen it is getting reduced by e raised to this. So then or you can say that pp divided by e raised to psi s by vt, and then your np should increase by e raised to psi s by vt, so that it will be same as pp np. Okay, so these two will cancel off. So one is with a minus sign, other is with plus sign. And what is np? So np is basically so this is also equal to ni square, and therefore np is equal to ni square by pp, which is basically na. So you can substitute that ni square by na into e raised to psi s by vt. So now if I substitute everything, I have the value 1.5 into 10 raised to 10 per centimeter cube whole square divided by 10 raised to 16 per centimeter cube. So you will have 1 centimeter cube will cancel off, per centimeter cube will cancel off, and only one of them will remain, and then multiply it with e raised to 100 by 26. So this will come around as 10 raised to 6. So let me put the unit also per centimeter cube here. 10 raised to 6 per centimeter cube. It is going to be very less because ni square by na is going to be of the order of 10 raised to 4, and this factor is of the order of 100. So 10 raised to 4 will go to 10 raised to 6. Similarly here 10 raised to 16 is going to 10 raised to 14, because this factor is going to be like 1 by 100. Okay, so this is like of the order of 1 by 100. Here it is of the order of 100. Okay, so usually we say that if there is 60 volt change, then 60 millivolt change correspond to multiplying by a factor of 10, because that's just a side note. Let me say e raised to 60 by 26, so that comes around as 10. So if it is 120 by 26, you will get 100. So every change of voltage by 60 millivolt will result in that's how this function changes. By a factor of 10 it changes when there is a linear change of 60 millivolt. Okay, so that's just a side thing. So we solved for case 1. Now what about case 2? So same thing, but it is now for 200. So for case 2, PPS is basically 10 raised to 16 into e raised to minus 200 by 26, and that comes around as 4.56 into 10 raised to 12 per centimeter cube. And then similarly NPS is going to be, if you calculate again, 1.5 into 10 raised to 10 whole square divided by 10 raised to 16 into e raised to 200 by 26, you will get, okay, so everything is per centimeter cube. So you will get this as 4.93 into 10 raised to 7. So 200 is like 3 times 60, right? I mean 180, 3 into 60 is 180. So you will get around 10 into 10 into 10. So that is like more than 1000. By a factor of 1000 you multiply. Okay, so now the important thing is the other part of the problem. So it is also asked not only to find out the concentration, but also the charge density rho at the surface. Now what is charge density? So how do you find out? So what are the charges here? We are going to have at the interface. Okay, so this is at the surface, or say semiconductor surface. So what are the contributors to charge? One is the acceptor ions. Okay, so they are there and they have negative charge. So per centimeter cube, if I write the charge, so this is going to be everything is going to be multiplied by Q. So this is the number density. Na is the number density. Since they are acceptor ions, I am putting a negative charge. So Q is taken as positive here. Okay, so this is the magnitude. So what else? We have those holes and PPS and NPS. Okay, they are there, and PPS, they have positive charge, so we need to add this PPS, then subtract the electrons, free electrons are there, NPS. So this is all what we need to find out. So you have the number density. We don't have any donor impurity ions, so we don't need that. Otherwise there should be a plus Nd will come, but in this case it is just a p type doped with a single acceptor impurity atom, so which will, each one of that will give you a negative charge, and there are Na number of them per unit. So this is like coulomb per centimeter cube. Okay, so that is the unit. This many so let me write the unit also. Coulomb per centimeter cube. So if I evaluate this, so Q magnitude is 1.6 into 10 raised to minus 19 coulomb, and then inside the bracket I have minus 10 raised to 16. Then PPS, what was our value? Something like 10 raised to 14. 2.1 into 10 raised to 14. That is our PPS. So 2.1 into 10 raised to 14, and then electrons, they were very small, very negligible. Even if you don't write, it is fine because it is 10 raised to 6. So minus 10 raised to 6. So that is per centimeter cube. So coulomb per centimeter cube. So if you do this, now if you compare these two terms, the first and the second term are the most significant. The last term is like many orders of magnitude smaller, so if you want to include them, you have to put many zeros, right? So it's like this 10 raised to 14 plus 10, or 10 raised to 14 plus 10 raised to 6. If you are doing, it is like 10 raised to 14 will have some 14 zeros. Okay, so much now it is 12. So 1 2 3, so yeah, 1 2 3 4 5, so 4 5 3s are 15, so one should not be there. Okay, so like this, and then 10 raised to 6 means it's like you are adding somewhere here. Okay, 1 2 3 4 5 6 1 2, so yeah. So you see that when you add these two it doesn't make any difference like adding this quantity. It's like 0 0 0 0 0 0, and then you have a 1, then 6 zeros. So you see that so if you write in scientific way, it will like 1.00000000, something like this, 1 into 10 raised to 14. So that is just 10 raised to 14 itself. Okay, so that's very negligible. So these numbers, you need to have some idea how big they are, etc. And if you compare the first two terms, it's like 10 raised to 16 and 10 raised to, they are only by 2 orders of magnitude. So you can write like this. It will be something like 10 raised to 16. You can write it as 100 into 10 raised to 40, and then you have 2.1 into 10 raised to 40. So that will give you basically 102.1 into 10 raised to 40. And you can see that this is also a negligible difference. If you look at practically, 100 and 102 is basically very close. So in other words, the important point that to be noted is that it is very close to 10 raised to 16. Okay, so if you evaluate this, it is like actual number will come around like 1.566 into 10 raised to minus 3 coulomb per centimeter cube. So this is for case 1. Same thing you can do it for case 2. So this is for 1, and for 2 same exercise you do like 1.6 into 10 raised to minus 19 coulomb, multiplying again, this is 10 raised to 16, then you substitute this. This is to be like even more closer to 10 raised to 16 what is in the bracket, and then minus 4.93 into 10 raised to 7 per centimeter cube. So that will also come around as minus 1.599 into 10 raised to minus 3 coulomb per centimeter cube. So when you compare the two values for 1 and 2, they are quite closer, and they are actually dominated by this term. Okay, so whenever we have the charge density determined by the acceptor impurity ions, not the electrons and holes in the region, that is what we call as the depletion mode. Okay, so this is going to be true, very true in the depletion mode. But as you go to the other modes, that is like accumulation and inversion mode, then you will see that either electrons or holes, if you go to the accumulation mode, what happens, the hole concentration is going to tremendously increase. So let me show you how. Okay, so if I am going into the accumulation mode, my psi s is going to become negative. So then PPS is going to increase by a factor of 100. So if it is minus 100, psi s is given as minus 100, that means I am applying a negative voltage on the gate. So if I apply a negative voltage on the gate, then the picture is that the band bending is going to like the metal side, it is going to go up, and here these bending of the band will be in the opposite direction. So it will go like this, whole band will go up like this, which means that your Fermi level is like very close to the top of the valence band. making it like very heavily doped. I mean, the concentration of holes are going to be very, very large. It's much larger than your Na. Okay, so that is what we call as accumulation mode. Whereas the inversion, so inversion is of two types. One is called the weak inversion. So the modes of operation, let me just review what we earlier said. Modes of operation. Number one, accumulation. So in this particular case, when phi ms is equal to 0, in order to get accumulation, what we need to give, VGB should be less than 0. Second is depletion. So depletion mode, we have basically VGB between 0 and VTH. VGB between 0 and VTH. Now this you can split into two. One is like VGB and phi B, and the other is basically phi B, VGB and 2 phi B. Okay, so if you recollect what we earlier discussed, you will see that if the bending of band become phi B, like it is downward bending, but if it is exactly equal to phi B, then what happens is that your EI here will just coincide with the EFS. So that means at the interface we have intrinsic region. Any bending beyond that is going to make it n-type in the interface. Okay, so this region is called weak inversion, because in this voltages we have at the interface more electrons. NPS is going to be greater than PPS. Weak inversion. So weak inversion where NPS we have found out just now is going to be less than or greater than PPS. So here, though this is depletion mode, so this is like a so I will write it as when VGB is between 0 and phi B, you still have p-type material or p-type, the material is p-type near the interface, because your NPS is going to be lesser than PPS. Holes are still the majority carriers. And the third mode is basically, so in order to distinguish between weak inversion, we call it strong inversion. And for strong inversion, what we need is your VGB should be greater than VTH. Okay, so here I have made a mistake. This should be VTH. This should be VTH. So I am taking the voltage variation from 0 to VTH into two steps. One is from 0 to phi B, and the other is from phi B to VTH. Okay. Now I can say this relationship again in a different way in terms of my I should say, okay, so I think I have made a mistake. So here so VGB, this is correct, but these two categories is better to say in terms of if I write, you will understand. So psi S should be 0 between 0 and 5b, and then here it will be psi s between 5b and 2,5b. Okay, so what is the difference between VGB and VGB is the applied voltage. So that applied voltage will be partially dropped across oxide and the remaining will be dropped across the semiconductor interface. So the voltage drop across the semiconductor interface is psi s. Okay, so in our problem, the two voltages that we considered, that is 100 millivolt and 200 millivolt, they both were basically satisfying this condition. So it was in the depletion region, but not in the weak inversion. Okay, it has not yet made into n type near the interface, so it is still holes are the majority carriers. Okay, so that you can see by looking at this relationship. NPS was always lesser than, one case it was 10 raised to 6, another case it was 10 raised to 7, but it is much lesser than PPS, which was like 10 raised to 14 in the first case and 10 raised to 12 in the other case. So that's basically what we have done so far.
Sir,
Yes.
sir, in the above weak inversion of in a place of 2,5e, that will be VTH or 2,5e.
It will be 2,5b because I am using
Okay.
psi s. So VTH I specify with respect to VGB, like we need to apply a gate to bulk voltage which is greater than VTH, then only it will be considered as a strong inversion where you have a layer of electrons under the in the oxide region. But before reaching that voltage, what is going to happen, I am separating into two category by looking at the bending of bands near the interface. Okay, so if so we are considering the bending downward direction. Okay, this purple colored curves. So if the bending is very small, like here you can see that the EI is still above EFS. EI become equal to EFS at the interface when the bending is the phi s correspond to phi s. This is our q phi s correspond to q phi b, right? Q phi b is the difference between EI and EFS in the bulk. So when the bending here become equal to that difference, we reached we made the material intrinsic at the interface. Any bending which is little lesser than that is basically a case of phi s between 0 and phi b. If it is greater than phi b, we have made it in principle into n type material. Okay.
Okay, sir. Okay, sir. But in case of VGB, that will be VTH.
Yes, in case of VGB, that is
If we take
VTH. Yes,
VGB,
yes. That is VTH because that is the applied voltage that we give at the gate. You go back to the previous lecture where I have derived the expression for VTH. VTH is the value of VGB that you need to apply such that your psi s, okay, this thing, your psi s become equal to 2,5b. That's the definition of VTH. So psi s becoming 2,5b is same as VGB becoming VTH. Okay, so we'll stop here.